Welcome back. In our last lecture, we ended at JKMA equation, and we have also seen how x varies with time at a different temperature, at a particular temperature below the transformation equilibrium transformation temperature. Now, we would like to see how the Ttt diagram is plotted from those x versus time plot at different temperatures. And remember, we are in the regime of isothermal transformation. Now, if we, so this recap would talk about few other things what we have done in our previous lectures. And the Johnson-Mail-Abrahami equation JKMA, the general form is x equal to 1 minus exponential minus kT n. And we have talked about one particular condition, and the condition is constant nucleation rate, constant velocity or growth rate, and then 3D growth, and we have used I and V expression. And then we have gotten this formula, which is exponential minus pi by 3 I V Q T4. And now, if I, let us say, this is my, let us say in case of solidification, this is my melting temperature, I will go to this range and then make it liquid, the entire solid is transformed to liquid, and I take different temperatures and then try to plot. This is T1, this is T2, this is T3, this is T4, this is T5. So, I try to plot x versus time at different those T1, T2, T3, T4, T5 temperature. Since at T1, which is very close to Tm, nucleation rate is low, growth rate is very high, but combining these two I and V, this I and V, the x would start at a much higher time duration. The incubation time would be very high. So, x plot would be like this, where this is 100% and this is 0%. And we are assuming that we can measure up to 1%, minimum 1%. For example, if the transformation product is less than 1%, we would say that the transformation has not taken place. And that depends on what sort of experimental techniques you are using for getting a measurement of fraction transformed. If you use a very sophisticated technique, then you can also go to a very low transformation amount to be your transformed fraction. You can go to 10 to the minus 2, 10 to the minus 3, all those levels. But if you use optical, simple optical technique, you can measure up to 1%, less than 1% it will be an error. So, 1% is considered to be a kind of fraction which we can measure. Now, this I can consider to be 1%, where I can see a kind of measurable amount. This is at temperature T1. If we try to plot at temperature T2, growth rate is still very high, nucleation rate is becoming little higher. So, the transformation would start little early. But interestingly, since both those things are having little higher value, the slope is changing. This green slope has changed, which has become little steeper. This also we have explained in our previous lectures. Now, as we go to T3, it's still in the regime. For example, if we try to plot I versus I and V, which is the growth velocity, this is Tm, growth rate values like this, nucleation rate values like this is I, this is U. I can see as we are going towards around T3, we are getting to this zone. So, that means we have sufficient growth rate as our nucleation rate, and the system would start little early. The plot would be like this. This is T2, this is T1, sorry T3. And now, if I try to go down further, for example, this way, then again at T4, if I find the T4 region here, I see that growth rate has gone down, but nucleation rate is very high. What does it mean? Means we have many more nucleus, but since the growth rate is small, so we would end up getting very fine structure. And that time again, since the growth rate is slow, again this particular slope, this slope would start tilting towards right, it would become shallower. So, then again this particular point would start little on the right side. So, if I try to plot that, it will be like this. This is T4. And T5, if I see, for example, if I plot it with this, T5 is here, where this is T5, this is T4, this is T3, this is T2, and let us say this is T1. Again I see that growth rate and nucleation rate both are very slow. So, that means again it will shift, this point would shift towards right, and the plot would become, again it would fall down, the slope becomes less steeper. Now, if we try to see and try to take those points on those axis, temperature axis, that means this is my T1, this is T2, this is T3, this is T4, and this is T5. Now, I will just take down 1% transformation point and 99% transformation point, which is this point, close to 100%. That time, let us say this was the T1, this one T1. So, this point, let us say here, and then this was here. Now, then T2 and then T2 here, T3 and then start point was, sorry, we made a mistake, and T1 is deleted. So, this is T1, let us say. Now, T2 we have taken the right one, T3 we have to take it down. So, this was T3, and the T3 plot is this one, okay. So, now if I take it down, this is, and this T1 start point is this one, T3 start point, okay. Now, again we have to go back to T4. The T4 start point is this one, which is shifting towards right again, and this is the end point of T4, which is here. And again, now finally again we are going to T5. T5 is start point is this one, and then T5 end point is this one. So now we have the locus points. This is 1 at T1, this is at T1, this is at T2, this is at T3, this is at T4, this is at T5. Now, if we try to connect those start points and end points, the start point indicates 1% is basically the start point, that means transformation start point, and 99% is the transformation end point. This is transformation. Now, if we connect them, then we will get a curve like this, and here also curve like this. So, now if you see, this is temperature and time, and it is taking a shape of C, which is also called C curve, and since we are doing it at a constant temperature, which is also we are following isothermal mode of experiments, that is what it is called, isothermal C curve, also isothermal transformation curve, and this is popularly known as Ttt diagram. We have also looked into these aspects in phase 1, but interestingly mostly this is in case of single component system. And also we have looked at the aspects, like if we have a Ttt diagram like this is 99%, this is 1%. We can accordingly draw different other points which are corresponding to, let us say this is 10%, this is 70%, like that way we can have different other Ttt diagrams, and this is temperature and time. And here if it is a liquid, this is the critical point which we call it as nose. And if the metal is taken on the left side of the nose gradually to the low temperatures, when you cool a liquid metal like this way, which will not touch those lines if that liquid metal does not touch, that means you are not getting any solidification. But when you take that liquid metal below melting point, the metal viscosity goes up. As the metal viscosity goes up, it becomes thicker and thicker melt. But at certain point, for example, if I try to plot viscosity as a function of temperature, and if this is my Tm, initially viscosity increase would be sluggish, and suddenly close to certain temperature it jumps and reaches to the viscosity of 10 to the power 13 to 14 Pascal second. And these temperature we call it Tg, or glass transformation. Temperature. And now if we follow different heat treatment process, for example, let us say I want to have only 70% solid phase and rest of the phase should be liquid, since glass is also a vitrified liquid. So, if we do this particular, for example, at this temperature T1, if we cool it down very quickly and then hold it to this level. So, once it touches 70%, that means it is converting into 70% of solid, and then suddenly we quench it to this level. So, that means that liquid is not allowed to crystallize anymore. So, you can have a fraction of 70% solid and rest liquid, and that liquid would stay as a glass mode. So, that way one can make, by doing that heat treatment sequence, that means this is the temperature, that means the temperature is, let us say, T1, time is, what is the time duration? So, this is the time axis, that means this is my time duration, this much time I have to, that means this is convert in T1, T1 time I have to lapse, and then I have to quench. So, that means this is my heat treatment sequence in order to get 70% solid plus 30% glass. Since and there is a temperature which is called Tg, if the metal is taken below Tg like this way, then we get glass. So, that means on this basis we can design how to have a different fractions of glass and amorphous phase. In polymer generally this gives an effect. In case of metals, we have a system called metallic glass, where you can do this kind of heat treatment in order to get different fraction of solid in glassy matrix. And the researchers have shown that sometimes in some metallic glass system, partial crystalline, that means some fraction of total phase is solid and some fraction is glass, then we have better property in terms of mechanical, in terms of magnetic, in terms of surface properties like corrosion, those kind of thing can be improved. So, according to our need, we can do the heat treatment on the basis of Ttt diagram. This is the thing we have also done in our phase 1. Now, apart from that, we have also seen different other variations. For example, in case of JKMA equation, we have seen different other situations. For example, in case of N, if we try to see, we see that N varies, let us say I have two different segments. One is site saturation plus constant V growth rate, and in this case if it is constant nucleation plus constant growth, N varies like this. If it is 3D, then here it is 4, here it is 3, this is the variation of N, and if it is 2D, here it is 3, here it is 2, and 1D it is 2, it is 1. So, these calculations as well as problems were discussed in our phase 1. But interestingly, if you see this, we are only talking about isothermal transformation diagram, which is TTT. And in our next phase, we will also talk about another diagram which is also very critical from the point of heat treatment. For example, here we have decided this heat treatment cycle as per the isothermal way. For example, everywhere I am quenching to some certain temperature and then holding certain time and then again quenching. So, we are doing those transformation isothermally. But one transformation can happen like this, then we have to decide that what will be the amount of transformation. But since these diagrams, the C diagram, C curves have been drawn on the basis of isothermal transformation, they will no more be valid for this continuous cooling. This C curve is to be modified a bit, and the CCT diagram, we end up getting CCT diagram which is continuous cooling transformation diagram that would also take a shape of C, but how to get there we will have to handle, and that in this phase we will do that, and that is more suitable for many practical heat treatments, mainly in steel heat treatment. We do have to use the CCT diagram information. Then we have also looked into binary system, and here we mainly talked about precipitation. And while taking the precipitation into our treatment, we briefly discussed how to derive a binary phase diagram, isomorphous, and eutectic. These two phase diagrams have been derived, and we had to do the derivation in order to have some idea how this precipitation is taken care of, mainly the overall transformation kinetics in case of precipitation. And there we actually considered a phase diagram which looks like this, and this is the beta phase, this is alpha phase, this is alpha plus beta, and here it is temperature, and this is percentage B. And here we are considering A and B solution. And when we considered this particular phase diagram, we try to treat it from the point of nucleation rate as well as growth rate. And that time nucleation rate also takes a form like this, and growth rate takes a form like this form, where this is my x0, that means this is the alloy composition we have chosen, and this is the temperature we are trying to see. Let us say this is my T1, what are the variations of I and V, growth velocity, and this is the point which is xc, and this is the point x beta. And here we stepped into a solid state transformation where the precipitation is observed. You can also have precipitation in case of liquid, but mainly we are concerned here with the solid. That case, this delta Gm is nothing but again activation energy per atom jump. Delta G star is also takes this shape, this form, where delta G is also volumetric term, but in case of solid-solid transformation, we have to also take care of another free energy change, which is the strain free energy change, apart from volumetric free energy change. The volumetric free energy change is all the time negative, but the strain free energy change is positive because it actually increases the energy of the system if something is strained, getting strained. It is natural because anything gets strained, it is the energy level of it increases. So, this particular term is written as this way, and both the term are volumetric term. And whenever we have this form, it is based on a spherical growth of the product phase. But the spherical growth can happen like this. For example, if this is the interface, this is the grain boundary of alpha. Let us say we have alpha phase in the beginning. If we try to see the alpha phase, diagram can look like this, where this is alpha grains. And if we try to locate at this point, this is the grain boundary of alpha alpha, and there we can have beta formation like this, or we can have beta formation there. Like that way, this beta can form at grain boundaries, grain corners, triple point, and then accordingly we can treat it like this. This is a lens sept. So, this is the sphere, this another sphere is growing, and we have also done those treatments. So, this is my R of that particular sphere. So, we have done that treatment also in our previous lectures. And using this I and V expression, we will also end up getting JKMA, and which is the general form is x equal to 1 minus exponential minus kt to the power n. And there k has got the term I and V, and this n is the exponent, time exponent, and t is the time, which is again the isothermal condition, but it can also be tweaked little bit to get into the non-isothermal regime, which will consider the rate of cooling. And in this next phase, we will also look at that part also. Now, this is another treatment we have done, and we have done some calculations also. And finally, we have gotten into diffusion and surface hardening, mainly carburization and decarburization. And in case of surface hardening, carburization and decarburization, we actually solved diffusion equation. And the general form of that solution is C x t, x is basically here is the distance, equal to a plus b error function x by 2 root over dt, where x is the distance, t is the time, and error function, finding this value from the knowledge of d, we can get error function, and then from boundary conditions we can get these constant values. And let us say two blocks are joined, this is C1 side, this is C2 side, then this diffusion path will look like this. And from the point, from that boundary condition, for example, x equal to 0, t equal to t, or x equal to x, t equal to 0, all those boundary conditions we can use to get to the knowledge of A and B and try to find out how long it takes, for example, in case of carburization, how long it would take for a particular condition to have a, let us say, a 50 micron case depth of carburized layer. Or when you do heat treatment in furnace, there will be always a possibility of decarburization in case of steel. And if we keep, let us say, 900 degrees Celsius, a particular steel composition, a particular carbon percentage, we keep it for a certain time, we can also calculate what is the decarburization case depth solving this equation. So, this one also we looked at in our previous lecture. So, now since we have done the recap of what we have done in our last phase, phase 1, it will be now easy for us to go to the next phase. So, in our next lecture onward, we will start looking at what we will be doing in our next phase, that means this phase, which is phase 2. Thank you very much.